Happy Thursday. Thursday, is this, I believe we're in week 6. So we have total of 8 weeks. We're at the end of week 6. So this week we've got chapter 9. Hello, Edith. I see you coming in. So this week we're doing chapter 9, and then next week we'll do chapter 10. That'll be the end of the new material. Chapter 10 is the end of the new material. So week 8 is usually I don't make the test 3 and the final project due the same week during a normal term, but because we're an abbreviated term with 3 weeks less than usual, the last test and the final project are due the same week. So next week will be the last of our regular Zoom meetings, which is great because next week I go back to the high school. So it's nice that we're kind of wrapping this class up as that one's ramping up. So we're going to do 9.2 today. So we're going to be using some concepts from 8.1. We're going to be talking about the sampling distributions of mean. We're going to learn a new thing. We're going to learn about t-values and t-distributions. These are very similar to z-scores and used the same way, but they have like specific criteria that we use to use t-values instead. We're going to be constructing confidence intervals as we did with 9.1, but we're going to be using means. And then at the end, we will determine the sample sizes that we need, just like we did with proportions. So after that, we will do lab 5. Lab 5 is super quick. So it will be using it'll be using the tools that we used in lab 3. Wait. No, lab 2, sorry. It'll be using the same tools we used in lab 2, but we're going to add a little bit of extra to it. So if you have your continuous data from lab 1 and lab 2, then it will be super quick and it'll be a super quick lab for you. It'll probably take you less than 10 minutes. So that's today. We're going to get that going, and it should not be, I'm guessing it'll be maybe slightly more than an hour tonight. It'll be short. As I said, we're tapering off the end of the term, not having as long classes so you have time to work on your final project. All right. So with our proportions, we determined that a point estimate, we did that where we did the number of successes over the total samples or the sample size. A point estimate for mean is just whatever the mean is of our sample. So our sample mean is just our point estimate. So if it asked you for a point estimate, it's just the sample mean. And we're going to use that sample mean to estimate the population mean. So the difference uh, with this unit as opposed to 8 is that we're not going to have the population mean and standard deviation as much. So we won't have it as frequently. So that's part of the reason that we're going to have to be using t-values instead of z-values is because we're not going to know population information. So our sample is going to be all we have. So remember the pennies. So we have pennies minted after 1982. They're made from 97.5% zinc and 2.5% copper. And here is the weight of 17 pennies that we randomly grabbed. And we're going to estimate the population mean. So all we do is we just add them all together, divide by 17. So our point estimate would be 2.464. And I think that the actual mean was 2.46. So this is a pretty good estimate. But in today's lesson, we're not going to know the population. So that's why we're going to have to do our confidence intervals. As with proportions, if we don't know the information about the whole population, we have to do a confidence interval to try to grab in that interval what our population is. We usually will round our statistics to 1 decimal farther than the raw value or whatever MyOpenMath tells you to do. So here, my raw data is 2 decimal points. So I'm going to round to 3. So that's all the point estimate is. It is just the sample mean, and it's just calculated like the mean. This one is not complicated at all. All right. Okay. So this is, I'm going to talk about t-distributions. Now, I'm not going to ask you to explain the difference between a t-distribution and a z-distribution, or a t-value and a z-value. I'm not going to ask you to give me that information, and I'm going to make it pretty simple. If we're dealing with mean, we're going to use t. If you're dealing with proportions, you're going to use z. It is a little more complicated than that in the real world, but um, you're not going to go wrong by using a t-distribution instead of a z-distribution. It's using t-scores instead of z-scores. If you're dealing with the mean, it's not going to hurt. So if you're dealing with mean, just use t-scores, t-values. So if you go on to 244, you'll go a little bit more in depth on how to choose one over the other. But 99% of the time when we're dealing with means, because we don't have the population information, 99% of the time we're going to use t-scores. So in order to calculate a t-score, um, you calculate it the same way that we calculate a z-score. So you remember z-scores. Z-score was our x our a z-score was our data value minus the mean over the standard deviation, right? So now with our t-value, it's basically the same thing, but we're going to take the sample mean, and if we have the population mean, you'll subtract the population mean, and this right here, it may look familiar, it should look familiar. It is that new standard deviation. The reason it is an S instead of a sigma is because it is a sample standard deviation. So it's the standard deviation of our sample. Because there's no reason to even do this if we know the population sample size. And don't worry about this yet. Actually, I'm going to tell you about it right now, but what it says when the t-distribution, it follows n-1 degrees of freedom. What this means is that when we put the sample size in our standard deviation, we are going to subtract 1 from our sample size. Now, you may recall way, way back, I think it was week 2, when we calculated standard deviation by hand. Remember that? I mean, it was traumatic for a few of you. When we calculate a sample standard deviation, we divide by n-1. You divide by 1 less than the sample size. We did this because there's so much variability in samples that we want to account for that variability, kind of err on the side of caution. And that's kind of what we're doing here. Because we're dealing with samples with our t-values, we use n-1 instead of n when we're finding our t-values. I'm going to have a whole table and calculator functions and all of that. So just keep that in your head and we'll discuss it again in a minute. All right. So this super similar. If I had the population information, I would be getting a z-score. But because I'm dealing with sample information, sample values, I am getting a t-value. I'm going to show you the difference between a t-value and a z-value. Now, this is not stuff that is super important for you to remember. The math that we're going to do later on is what's super important to remember. This is just kind of giving you some background. Okay. So here's my histogram for Z. It is pretty normal and it's not very spread out. Notice it's kind of all tight there in the center, and it's a pretty decent bell curve. Here's T. Notice the big difference here. So notice that there's not a whole lot going on in the tails. Here, I have a little bit more in the tails than I do with Z. So it's not quite as perfect of a bell curve, but it's pretty close. But it's just slightly more spread out. And there's nothing wrong with that. It is perfectly fine. And a big part of this reason is we generally use t-values or t-scores, t-value, whatever you want to call it. We generally use those when we're dealing with smaller sample sizes. You know, like the things that we were mentioning before, when the sample size gets bigger, we get more and more normal. So when we're dealing with smaller sample size, it's a little bit harder to estimate the population because our sample sizes are smaller, and that's kind of why we use t-values. It accounts for that smaller sample size. All right. The histogram for Z is symmetric and bell-shaped. The center is at 0. Pretty much everything is between -3 and 3 standard deviations away from the mean or Z scores. It follows a standard normal distribution. With the t-value, it's also symmetric. The distribution has longer tails. It doesn't follow a standard normal distribution. Remember, our standard normal distribution was when we converted all of our data values to z-scores. That was the standard normal distribution. It doesn't follow it says unlikely because the thing about t-values, as my sample size gets bigger, the histogram for t-values is going to get closer to a z-score. In fact, my t-score becomes a z-score when the sample size gets really large. Then they become exactly the same thing. Okay. The spread can be attributed to the fact that we are using a sample standard deviation instead of a population. So because the sample standard deviation is a random variable, it's not constant because it's not based on population, it's based on whatever sample we have. Because it is based on that sample and it varies more, we have more dispersion, it's spread out more. Now, as I said, you don't have to remember all this, it's just kind of get into your head what it is and why we're using it. Okay, these are the properties. I'm not going to ask you to reiterate these to me, so just kind of nod your head and smile and as I go through them. So the t-distribution is different for different degrees of freedom. Degrees of freedom, think sample size. Goes a little deeper than that, but not for what we're doing. It is centered around the 0 and it is symmetric around 0, just like z-scores. The area under the curve is 1, just like z-scores. As it increases and it decreases without bound, it will approach but never equal 0, just like z-scores. This is the difference right here. The area in the tails is a little bit greater than the area in the tails when we're dealing with z-scores. Because we're dealing with samples, the area in the tails is going to be a little bit more. I'm not going to give you new percents, but it would be a little bit different than our empirical rule. Remember, our empirical rule was 95% or within one standard deviation, or sorry, 68% within one, 95 within two, 99.7 within three. It would be a little bit different, but we're not even going to get into that. We do not need to revisit that. But as our sample size increases, we become closer and closer to the standard normal curve. As my sample size increases, we get closer and closer to z-scores. So if I'm doing one of these and I have a sample size of 1,000, I'm still going to look up the t-value, but it's going to be the same thing as the z-score. And I think it's around 40, 45, maybe 50 that they become equal. I can't remember I mean, it's probably different with every distribution, but right around the sample sizes of 45 or 50, my z-scores and my t-scores become exactly the same. So sample size really makes it different with t-distributions because larger sample sizes are going to have means and standard deviations that are closer to the actual population mean and standard deviation. It's that law of large numbers. We talked about that before. All right. This is kind of showing you the difference. So the orange one there, if I have a sample size of 5, you can see my tails over here are a little bit fatter. Sample size 15, it's getting closer. My tails are getting less fat and it's rising up closer to the normal curve. And yeah, if I went even higher, if I went to 45, it would be exactly the same thing as the normal curve. All right, so the difference with t-values. So you know z-scores, it's always left, right? The left tail. So my z-scores are less than or equal to. For some reason, somebody decided that t-values need to be greater than or equal to. I don't know who decided that. I was not on that committee, but this is what they do. And that area is the alpha. So my greater than or equal to here is the alpha. So if I'm doing a confidence interval kind of with z's, I would have alpha divided by 2 and alpha divided by 2 if I had my center something percent. We did this on Tuesday, so it's similar. So you would do alpha by divided by 2 on both tails. But yeah, the t table that we're going to be looking at and the inverse t that we're going to be using in our calculator, it does the right side. Not that yeah, it's just weird. Okay. So let's start finding our t values. We are not going to be doing n minus 1 degrees of freedom for these t values. We're going to be using the t table just straight with just n instead of n minus 1. So we want to find the t value such that the area under the t distribution to the right is 0.2, and we're going to have 10 degrees of freedom. So let's show you the table. The table here looks a little bit different than ours. I'm going to show you here, and then I'm going to show you our table. Okay, so degrees of freedom is going to be in this column right here. This is your sample size. This column, it says DF, says DF right on the top. That column on the left is your degrees of freedom, your sample size. So here's my sample size 10, and we're looking for 0.2. So we're looking at one tail because this is one tail of our curve. So I'm looking at 0.2. So look right here. So with 10 degrees of freedom, my t value is 0.879. Now ours looks slightly different. I will show you. So this is my z table that we've been looking at. The second page. The second page is the t distribution. So you just flip it over or scroll down. Degrees of freedom are over here on the left. Here's all my degrees of freedom. So this is my sample size, and area in the right tail are up here at the top. Okay, so I'm going to go 10 degrees of freedom, and I'm going to come over here to get to 0.2. Did I go too far? I went too far. Here's 10 degrees of freedom. 0.2 is right here, 0.879. So just degrees of freedom, this is your sample size. Notice how when I scroll down here, when I get to 40, it starts jumping 40, 50, but look at the difference. If I'm looking at 0.25, between 40 and 50, there's only 0.02 difference. Look, 50 and 60 are exactly the same here. 50 and 60 up here are 1,000, or 50 and 60 here are 1,000th. So as I said, it's going to start approaching what that z-score is. And I believe we have an example that requires us to go down here, and I'll show you what to do with that. Plus, I'm going to show you how to use your calculator to find these. But I know that some of the TI-83s don't have the inverse T capability. So you might have to, if you have a TI-83, you'll probably have to use the T table, which thankfully it's a pretty easy table to use. Okay, let's go back. All right, so let's find another one. Find the t value such that the area under the t distribution to the right of the t value is 0.05, assuming 15 degrees of freedom. All right, so I'm going to go back over here, make it a little smaller so I can see the top. 15 degrees of freedom, so right here. 0.05 is right here. So my t value, I'm going to write it down. My t value is 1.753. All right. Bet you would like to see how to find these in your calculator. I mean, I like the table. I actually go to the table before my calculator. This is one of the few tables I actually really like, and I don't know why. It's just comforting to me. All right. Here's my calculator. I'm going to find the same one that I just did. 0.05 is my alpha, 15 degrees of freedom. So these are distributions, a T distribution. So it's going to be in the distribution section. So you're going to do second vars because that's our distributions. The blue is distributions. Remember inverse norm? Right underneath of it is inverse T. The area is that alpha. So 0.05. And my degrees of freedom is my sample size. It's really this simple. Paste. And this is what it would look like if you don't have that screen that I have. And it gives me a negative, but that's okay. We know that our T values are positives. So you just nod your head and smile and just write down a positive number. So we know they're positive, so just use the positive. So it says 1.753. I had 1.753. We're good to go. So inverse T it's super helpful, especially if you get one of the larger numbers, like down here. If I got 43, I can probably estimate it just fine because they're super close to each other. But using my calculator, it's going to give me the exact number. So we're going to be good. All right. That's not where we want to be. That's our lab. Okay. Let's move on. Okay. Confidence intervals. So the first thing that we look for with our confidence intervals is we want to make sure that it comes from I realize that we have a delay. Usually by the end of class, it seems like my delay is not quite as bad. I don't know why it starts off so bad. Okay. So the first thing that we look for when we're constructing our confidence interval is, did my data, my sample, come from a simple random sample or a randomized experiment? If it doesn't say in the problem that it came from a simple random sample, you need to write down that we are assuming it comes from a simple random sample. Obviously, MyOpenMath's just going to give you the math and you're just going to do it. But if you were doing a whole problem on your own, or you're going to say that we are assuming a simple random sample. Now, if you decided to do a confidence interval on your final project, I'm not expecting you to have simple random samples on your final project. I'm not expecting that at all. So if you decided to do one of these, you would just say, we're pretending it's a simple random sample, or say it's not a simple random sample, but I'm still choosing to use this method of analysis or whatever. So just acknowledge that it should be a simple random sample, but I'm not going to mark you down for not using one, if that makes sense. Okay. Our sample size needs to be less than 5% of our population. The data needs to come from a population that is normally distributed, or a sample size needs to be large. So our sample size would need to be greater than or equal to 30 if it is not a normally distributed population. So if our population is not normally distributed, our sample size needs to be greater than or equal to 30. So it should state whether or not it's normally distributed. So this is the central limit theorem. I think I mentioned the central limit theorem before. I'm not requiring you to remember what it is or to say this back to me, but that's what the theorem is. The central limit theorem tells me that a population that is not normal becomes normal with larger sample size, typically greater than 30. That's what the central limit theorem tells me. Now, I'm not going to mark you down if you don't say that it's because of the central limit theorem that you can use this. I'm not going to mark you down for that. So no worries. Okay. So here's how we calculate the lower and upper bounds of our confidence interval. This is it's not exactly, but it's basically the same formula that we used for proportions. This T value is instead of our Z-score. And it's alpha divided by 2. So if I'm like a 90% confidence interval, my alpha would be 0.1. You divide it in half, I'd use 0.05 to find my T value. We're going to use n minus 1 degrees of freedom. So you'll subtract 1 from the sample size when you're looking for that T value. This right here This right here is standard deviation or standard error. So just like with our proportions, you take your t-value or your t-score and you multiply it by the standard deviation because it's going to tell you, the t-score tells you how many standard deviations away from the mean the edge of my confidence interval is. And then so you take that value and multiply it by that standard deviation, and it'll give you the edges, the boundaries of my confidence interval. But remember, because we're dealing with samples, we have to use n-1 degrees of freedom. Any questions before we do math? Okay, let's move on. All right. So this is the sample that we just did earlier. If I found the mean and the standard deviation of this sample, this is what I would have. Oops, this is what I have for the mean and the standard deviation of this sample. Now, we need to use the new standard deviation. We can't use this one. So don't forget that piece. So let's do all of our things to get our confidence interval. So the first thing, is it a simple random sample? It told us it was on the last slide that we had. It said this is a simple random sample. I'm just going to write that up here. If you want to write SRS, that works also. Everybody in stats land knows what an SRS is. And I would say 17 pennies is, wait. There's no square, no, because we're calculating the standard deviation normal on this one. For the only place we're doing n-1 is to get the t-score, the t-value. That's the only place we're doing n-1. Yeah. Good question. That was a great question. Oh, so for those of you on recording, she asked, even though it says square root of n, is it actually square root of n-1? And it's not, because the n-1 only refers to the t-value. That was a great question. Okay, so our sample is less than or equal to 5% of the population. Therefore, we have independence. So it is independent because our sample is less than 5% of the population. That's good. Okay, so now I need to calculate. I need to get our t-value, and I'm going to need to get our standard deviation. Okay, my t-value, wait, 99% confidence interval, just a second here. So 0.99, 1 minus 0.99 is 0.01. So I'm going to take 0.01 divided by 2, 0.005. This is what we're going to look for on the top of our sheet. That is going to be our alpha divided by 2. Okay. So my t sub alpha divided by 2, let's take a look. Our sample size was 17, 2, 4, 6, 8, 10, 12, 14, yeah, 17. So I'm going to go right here to 16. Because our sample size was 17, we do n-1, we go to 16, and I'm going to go over to 0.005. Right here, 2.921. So this column up here tells me the alpha, or the alpha divided by 2, and the sample size is here. So we do 2.921. So that's our t-value. Now I need my standard deviation. So I'm going to do S sub x bar because this is a sample. So it's S, and that is 0.02 divided by square root of 17. Use my little calculator. Approximately, this is small, 0.0049. That is teeny tiny. All right. So now that we have our t-value and our standard deviation, which is our new standard deviation or standard error. Now I can calculate the margin of error. So my margin of error is going to be the t-value times sigma sub x bar, or sorry, s sub x bar. So I have 2.921 times 0.0049. All right, I have my margin of error is 0. I'm just do 0.014. We're just going to go there. So my margin of error is 0.014. Okay, that was a lot of work. Y'all hung in there. Good job. So now all I need to do is I need to write my conclusion. There's two different ways that we can do this. I can do that plus or minus my margin of error, which would give me 2.464 plus or minus 0.014, or I can do lower, comma, upper. 2.464 minus 2.4, I'm going to just do 2.45 because rounding is tricky there. Then 2.464 plus 2.48. Okay. I'm going to say the words that are going to help you here. So we are 99% confident that the actual mean weight of pennies minted after 1982 is 2.464 plus or minus 0.014. Is this grams? Grams. Make sure you use your units. So the other way that we would say this is we are 99% confident that the actual average weight of pennies minted after 1982 are between 2.45 and 2.48 grams. So what we're doing is we're estimating the population mean. Because we don't have the population mean, we can't we can't take every single penny out there and weigh them. We're estimating what that population mean will be. And it's going to be somewhere between those two values. So it's 2.464 grams plus or minus 0.014 grams. So it's somewhere in that interval. Questions before we move on? We've got another one and a calculator function. You're like, I just want the calculator function. It's all right. I use the calculator function. They did the same math we did, except for they rounded to 3 decimal places, but I was being lazy. So we're 99% confident that the mean weight of pennies minted after 1982 is between 2.450 and 2.478 grams. That's basically what I did. I just was lazy. That's our conclusion, and that's basically how you would write it. This is a great template. It's a great template of how you would write it. I would like you to like put the word actual, maybe like right here, actual, or you can say the population. I would like one or the other of those words in there because this is a little bit more vague about what we're referring to. So say the actual mean weight of pennies or say the population mean weight of pennies. If you can put one of those words in there, that'd make me happy. Okay. Now, much of the time, you're just going to have a bunch of data and they're not going to give you the mean and the standard deviation of it. And you're just going to have a bunch of data. Like, for example, right here. This website, fueleconomy.gov, allows drivers to report the miles per gallon of their vehicle. This is for Ford Focus, 2011 Ford Focus. randomly selected 16 different owners and took their miles per gallon, so their reported miles per gallon. So if you are doing most of your work by hand, then you will use one variable statistics in your calculator to calculate the mean and the standard deviation. If otherwise, you would do that by hand, and that doesn't sound like any fun at all. So let's do that. Let's put this in our calculator. That's not the right side. Let's do this. And I'm hoping you remember how to do this. We do stat and then edit. Mine's already empty. If it's not empty, you go up to L1 and then you'd hit clear enter and it would clear it. So I'm just going to enter these in. Thankfully, it's not very large. Except for I'm slow. I'm gonna have to check for typos after I do this because I am typo queen. See, that was a typo 37.1. 7.3. Thirty 2, 9.6, 2. Oh, wait, 40. Okay. Got lost. There's 37, 36. Okay, I'm gonna go back and check for my typos because it happens. 35.7, 37.2, 34.1. Okay, I'm gonna give you all a minute to catch up. So if you wanted to calculate this by hand, you could just go into one variable statistics. So remember it's at stat, calc, and it's the first option. And then my list is in L1, leave frequency list blank. And you can go in here and it'll give you the mean and the standard deviation. Then you can hand calculate that standard deviation. I'm going to do this by hand and then I'm going to come back and show you how to do the calculator function. So this gives you, I'm going to write these down. So I have my X bar is 36.8. My standard deviation, we're using the sample standard deviation because this is a sample. So 2.92, go 1 decimal farther than our data. And my N equals 16. So I have 16 data values here. And so when we find our T-score, we're going to do N minus 1. So we'll do 15. Go back over. Well, that's the wrong way. Okay, go back over here. So I'm not going to write it down, but we have a simple random sample. It says that there. There's clearly 16 is less than 5% of the entire population. So we're good there. So I checked those things. Let's get our T value. So my T sub alpha divided by 2, my confidence interval is 95. So 1 minus 0.95 is 0.05. 0.05 divided by 2 is 0.025. So this is what I'm looking for on my T-table is 0.025. Okay, let's do the T-table. N minus 1 degrees of freedom. So we're going to do 15 because our sample size is 16. So here's 15, 0.025. Do not grab this first one. That's 0.25. Go all the way over here. Don't forget the 0. So my T value is 2.131. So that's 0.025, and we're using N minus 1 degrees of freedom. So we're at 15. 2.131. All right. My standard deviation, so the S sub X bar is going to be the sample standard deviation, 2.92, divided by the square root of 16. Let's put this in my fancy schmancy. Remember, we don't do n minus 1 for a standard deviation. Ooh, I love it when it's a nice pretty number. 0.73. All right. So margin of error, the way that we calculate margin of error is the t value, t sub alpha divided by 2, times the standard deviation. So my margin of error, 2.131 times 0.73. 1 point, let's do 1.56. Okay. So remember, we could do mean plus or minus standard of margin of error. I could do x bar plus or minus margin of error, which gives me 36.8 plus or minus 1.56, or can do lower, upper, which would be, makes me math, 36 minus, that didn't work, 36.8 minus 35.24, and then 36.8 plus my margin of error, 38.36. Okay, let me give you the interpretation of this. So we are 95% confident that the actual average miles per gallon for a 2011 Ford Focus is 36.8 miles per gallon plus or minus 1.56, or you can say 36.8 plus or minus 1.56 miles per gallon. Or we could say that we're 95% confident that the population mean of the miles per gallon for a 2011 Ford Focus is between 35.24 and 38.36 miles per gallon. Okay. You want to learn how to do this on the calculator? It's a little bit less math. Yes. Okay. So we use this function right here. So this is a test. A confidence interval is a test. So we're going to go to stat, test, and it's t interval. If you printed off the PowerPoint, this is probably already on there for you. There's two different ways that we can use the t interval function. There's two different ways depending on what you're given. Let me show you. That's not the right way. Okay. So I'm going to clear this out. So this is not a distribution. This is an interval, or this is a test. So we go stat, arrow over to tests, and t interval is number 8. Okay. Now, we use data if we put a list in our L1. If you're given a list of data values, we use data. If they give you a mean and a standard deviation, you'll use stats. So, I'm going to use stats first. So going back to the pennies, it says that my mean of my pennies was 2.464 and my standard deviation was 0.02, and then my sample size was 17 and my confidence level was 0.99. So this is if it gives you stats, if it gives you the information. So it gave me a mean, gave me a standard deviation. This is not your new standard deviation. This is actually the sample standard deviation. It's not the new one, the one you calculate. This is the actual standard deviation of your sample. There's my sample size, confidence level. There we go. And it gives you your confidence interval. And this is the same thing that we calculated. Okay, That's great. That's the same thing that we got. Now, since we have values in our list one for the Ford Focus, we're going to go over here to data. And it's going to calculate, it'll do the one variable statistics stuff for us. We don't have to do all of that calculation. And that's in list one. The frequency, it says one, just leave it at one. We don't want it to say anything other than one, just leave it there. The confidence level is how confident we are. It says we're at 99% here. We're going to be at 99%. Hit calculate. Bam. It gives me, oh, we weren't 99, it was 95. Sorry, I'm going to go back. I was on the wrong screen. Sorry about that. Yep, see, you got me. Go back and do this again one more time with feeling. All right, 95%. Thank you. There we go. So this gives me the standard deviation. What did we have here? 2.92. Yeah, this is correct. It gives me my mean, and then it gives me my confidence interval. My confidence intervals are basically the same. I just rounded. I rounded on my standard deviation. That's why it's slightly different. But this is beautiful. So much faster and easier than doing it by hand, isn't it? But it's really important to know how to do it by hand because then you know what your calculator's doing. And it's kind of gives you an idea, especially showing that we're taking a t-value and multiplying it by a standard deviation. It's very reminiscent of what we did back in, like, I don't know, z-scores chapter 7 and whatever other chapter we did z-scores. So it's kind of reminiscent of all of that stuff. So this gives you your interval. Now, sometimes it wants you to write it in the format of mean plus or minus your margin of error. If that's the case, this gives you the mean. So you would take your upper value right here and subtract the mean from it, and that's going to give you the margin of error. So I'm going to write this down on my screen and then let's see here, upper value minus X bar equals margin of error. I'm going to write these numbers down and so you can kind of see. 38.354 minus 36.8. Okay, let me pop back to my other screen. So you take that upper value, subtract the mean, and that's going to give you the margin of error. So if I do 38.354 minus 36.8, I get 1.554. I hate that there's that delay, but it's still, you can see it now. So you just take that upper value minus the mean, and it gives you the margin of error. This is what we got anyway. Because it might ask you to write it as X bar plus or minus margin of error. So just pay attention to how it wants you to put it in there, and make sure when you're putting confidence intervals in there, whether it's for 9.1 or 9.2, put the parentheses. I've had people in the past say, it keeps marking me wrong. It keeps marking me wrong. They weren't putting parentheses around it. So don't forget the parentheses. All right. Questions? The next thing we're doing is calculating sample size. So any questions on finding the confidence interval before we move on to sample size? Okay. All right. So this is just the margin of error formula. I just threw it there because I don't want you to forget it. So I took that margin of error formula and I did all of the math necessary to solve for n, kind of like I did with 9.1. So I solved for n, and I get this formula because I need to be able to calculate the sample size. So if I know the confidence level I want, like 95% or 99%, and I know the margin of error I want, like 3 miles per gallon or whatever, I need to figure out the sample size that I need. Now here, we don't need an estimate like we don't need a prior estimate like we did with proportions. We don't need that. But the issue is our t values are dependent on sample size, right? In order to find the t-value, we need to know the sample size, but we don't know the sample size. So here we're just going to use a z-score because our z-scores are not dependent on sample size. So we'll do exactly like we did in 9.1, and we'll divide the tails in half, and then we'll find the z-score that goes with it, and we will use that to find our sample size. So what this is the z-score times the standard deviation divided by margin of error, and then you square the whole thing. That will give you your sample size. Just like we did on Tuesday, you round the next highest whole number. Even if I ended up with a sample size of 201.01, you still would round it to 202. We round up, always round to the next higher whole number. Our sample size is always whole number because I can't poll 50% of a person. I can't. So it has to be a whole number. All right. Let's go back to the pennies. We need to know, and this S is my sample standard deviation. It's not the new standard error. That's just the sample standard deviation. Okay. How large of a sample would be required to estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with a 99% confidence? Okay. So 99% confidence, this right here, I need the z-score that goes with that, but it's z divided by, so z alpha divided by 2. 1 minus 0.99, 0.01, 0.01 divided by 2, we're looking at 0.005. This is the z-score I want, and our z-scores are always positive. So even if I get a negative in my calculator, I'm going to get positive. We are using inverse norm. So you do your second bars, go down to inverse norm, 0.005, leave 0 and 1 for the mean and the standard deviation. So 2.576, or your table down here. Oh, it's 2.575, I lied. Or your table right here. Just you can use this table. Remember those numbers? That's where we got that. Okay. Okay. So now I have the z-score. My S is 0.02. My margin of error, 0.005. So here's how we're going to set it up. N equals 2.575 times, oh, I don't like that, times 0.02 divided by 0.005 squared. If you are really careful with your parentheses, you can put this whole thing in the calculator at once. If you are parenthesis careful, otherwise do it piece by piece. Okay. 2.575 times 0.02 divided by 0.005 squared. Yes, good. Since we have always round up, our N is 107. So we would need to pool 107 pennies. So we would need 107 pennies. Questions on that? That's how big our sample size would be. We're going to do another one. Somebody's at my front door. That's really weird. Okay. My Ring doorbell. Yep, see here. They did the math here. I always do it by hand and walk you guys through it because I feel like that's the better learning. But the reason I still leave it printed on here is because people who print off the PowerPoints and maybe don't watch the videos super thoroughly, they can still show them the math. That's like why I still leave that there. All right. Back to the Ford Focus information. I'm going to go back to You see my calculator. So we have the mean or the standard deviation 2.917. Okay, so 2.917 was my standard deviation. For 95% confidence, 95% confidence is 1.96. So my Z sub alpha divided by 2 is 1.96. My margin of error is 0.5. I would love you to try this on your own. I'll work quietly behind you. I'll write the formula if it's helpful. That was really ugly. Okay. How'd we do? Yay! Good job. All right. So we would need to randomly select 131 Ford Focuses. I guess focuses, Ford Focuses, in order to, because see, the plural of focus in math is foci, but this is a Ford Focus, so I guess it's focuses, but I'm uncomfortable with that. All right, but we would need to randomly select 131 Ford Focuses, Ford foci, in order to get that confidence interval and the level of confidence. Any questions on these? So the next two slides, what I'm going to do is show you Tuesday compared to today, because sometimes people leave and they're like, wait a minute, how is what we did Tuesday different than today? What are the problems going to look like? What words should I look for? So I broke it down and I have them side by side comparisons so you can see the words. All right. So when we are calculating the confidence interval, here's the words you need to look for. Section 9.1, proportion. Look for the word proportion. That's so important. For 9.2, you're going to see the word mean. Very important. 9.2, you see mean. For 9.1, you see proportion. So obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty. 9.2, construct a 95% confidence interval for the mean miles per gallon of a 2011 Ford Focus. So those are the important words, proportion and then mean. All right, let's take a look at the next one. So this is when you're looking for the sample size. So when we're looking for a sample size, you're looking, your margin of error is going to be percentage points. It's going to be percentage points for 9.1. It's going to say within 3% or within 5 percentage points or something like that. It's going to have something to do with percent for your when you're looking for the sample size. It may or may not it may or may not talk about a previous survey, because if there's no previous survey, we just use 0.5. But if it does, then that's definitely a trigger that you're going to use that. So on 9.2, You're going to have, when you're talking about within something, it's going to have some units there. It's not going to be necessarily a percent. It's going to have some units there. And also the word mean will be there. You will have the mean and there's going to be some sort of units with it. So hopefully this helps. I'm going to do the same thing in chapter 10 because chapter 10, part of it deals with proportions and part of it deals with means. And so I'm going to do the same thing. I'll break those down. And I have a really good review slideshow also for chapter 10 that you can use for, you could actually print it off, write little notes on it, and it could be a study guide for you. All right. Any questions on this before I move on to lab 5? As I said, lab 5 is super fast. Maybe once you get to your homework, so make sure to message me when you're in your homework. Okay, so we're going to talk about lab 5. So lab 5, there it is. You are going to be using your continuous data from labs 1 and 2. So just use that continuous data. And if I didn't allow the continuous, like if I said, hey, that's not continuous, I actually really don't care at this point. Please do not collect more data. Use data that you used before, unless you, I mean, if you want to throw in some of your final project data, go for it. I don't care. You're absolutely can if you just say, hey, this might be interesting with my final project data. Go for it. I don't care. I don't care what data you're using as long as you have at least 20 data values. That's all I care about. Have at least 20 data values in there. I'm not going to grade you on whether it is correct as long as there's at least 20. All right. So you remember a long, long time ago in the land of Lab 2 when we used the descriptive statistics tool. It was that thing that we turned on, that analysis thing that we turned on. Hopefully you didn't turn that off. If you did, go back to week 2 or 3 or whenever we did that and watch that video again to figure out how to turn it back on because I'm not going through it right now. All right. So we're going to use that tool again, but we're going to do something slightly different. So I'm going to click on data and then I want the data analysis tool. Once again, we're going to do descriptive statistics and click OK. My input range is the same as it was before. It's going to be all of these data values that I have, the 5,847, not really. All of this, it's that data right there. My output range, as before, I want it to go in a box. So I'm just going to put it in this box. Okay, here's the things that we're doing. I do want summary statistics. The new thing we're clicking on, click on confidence level for mean. So this is going to give us a confidence interval. Well, it's going to help us create a confidence interval. You can choose whatever percent you want here. I'm going to have a 95% confidence interval. You might want a 99% one. You might want an 87. I don't care what you choose, just whatever you want. It defaults to 99 or 95. I'm just going to leave it there. And I click OK. It all goes in here. I'm going to spread it out so I can read it. Okay. This is all lovely. All the stuff that we had before, but we've got something new. This right here, I'm going to highlight right here. This right here is our margin of error. That's what that box is right there. It says confidence level 95%. That's the margin of error. You are going to use your Excel tools to put stuff over here. So in the margin of error box, I'm going to put equals, then click on this and hit enter. My margin of error is now in there. For mean, equal, click on the mean, hit enter. That I didn't mean to do that there. Delete that. Let's do it one more time with feeling. Equals, mean, enter. To get the lower bound, you do the mean minus the margin of error. So we're just going to math with it. I'm going to do equal the mean minus the margin of error. That gives me my lower bound. Upper bound is the mean plus the margin of error. So equals the mean plus margin of error. So now I have my two bounds right there. This is where most of your points lie. Yes, there's some points right here, and there's some points right here. Most of your points are in your interpretation. What am I estimating? So you need to answer this in context of your data. So if your raw data is about temperature, you're going to reference temperature here. Mine is magnitudes of earthquakes. I'm going to reference magnitudes of earthquakes here. If it was miles per gallon of cars, you're going to reference that here. What I'm estimating is the population mean earthquake magnitude. So you are estimating the population mean of something, or you can say the actual mean. I don't care if you say actual or population, but I want you to, that's what you're estimating. You're estimating the actual mean. I'm estimating the actual mean magnitude of earthquakes. That's what I'm estimating. Okay. How confident am I? I'm 95% confident. That's all you need to put there because that's my confidence level. That's all you need to put there. I am 95% confident. We're kind of scaffolding this, taking a little bit here, a little bit here, and here's where you're going to write your entire thing. I'm 95% confident that the actual average magnitude of earthquakes is between 6.86 and 7.23 on the Richter scale. There you go. You're going to answer it in context of what your variable is. You're going to use units, whatever your units are. If you're using temperature, you're going to say degrees. If you're using miles per gallon, you're going to do MPG. If you're doing height, you'll say inches or feet or meters or whatever. And you're going to use these values in your upper and lower bound. And that's it. There's your 10 points. That's your lab. Any questions on the lab? All right. So this is the end of everything I have for you today. And so any questions for on the recording? I know, Edith, you have questions for off the recording, but anybody have any questions for on the recording? All right, I'm going to turn that off.